Mercury, the planet that shouldn't exist. What if I told you that the closest planet to the Sun has ice? That the smallest planet has one of the biggest cores? That a planet that spins slowly still generates a magnetic field? That this tiny scorched world has been wrinkling like a raisin for billions of years? Meet Mercury, the planet that shouldn't exist, but does. Welcome to Cosmo Pulse, where we explore the mysteries of space and science with awe, curiosity, and a dose of the unexpected. Today we're diving deep into the paradox that is Mercury. If you enjoy turning science into wonder and the cosmos into curiosity, make sure to hit that subscribe button and join us every week. Mercury, the enigma of the solar system. Mercury, the tiny innermost planet, defies expectations at every turn. It's a world of extremes and contradictions. A problem child of the solar system, as one scientist quipped. Mercury is smaller than some moons, yet surprisingly dense and unlike any other rocky planet. Daytime on Mercury can bake the ground at 430 degrees Celsius, but just a night later it plunges to minus 180 degrees Celsius without any atmosphere to hold the heat. In fact, Mercury's daytime side is hot enough to melt lead, while ice likely lurks in craters at its poles. A baffling juxtaposition we'll explore. Even Mercury's orbit was so odd that 19th century astronomers scratched their heads over its wobble. It ultimately took Einstein's theory of relativity to explain Mercury's wayward perihelion drift, a historic puzzle that cemented Mercury's reputation as a rule breaker. This little planet, in short, shouldn't exist in its current form, yet here it is, challenging our theories of how planets form and behave. Mercury's giant iron heart. One of Mercury's most baffling features is its oversized iron core. Imagine a chocolate candy that's mostly filling and very little shell. That's Mercury. Roughly 85% of Mercury's radius is metal core, an iron heart that fills about 57% of the planet's volume. By comparison, Earth's core is only about 15% of Earth's volume. Mercury packs so much iron that scientists have likened it to a cannonball in space. It's the second densest planet after Earth, despite being the smallest, with a density of about 5.3 grams per cubic centimetre, far higher than you would expect for a body barely bigger than our moon. In fact, Mercury is 80% core by mass, essentially Earth's core without the rest of the planet around it. This giant iron heart is an outright anomaly. Why would the innermost planet end up mostly metal with only a thin, rocky skin? Scientists are intensely curious about how Mercury got this way. Did it form with extra iron or lose its rocky mantle somehow? We'll discuss the wild formation theories in a moment. Spoiler, think planetary collisions and even magnetic magic. But first, Mercury's core isn't just big, it's also partly molten and even has a solid center. NASA's MESSENGER mission measured Mercury's spin and gravity with exquisite precision and discovered that Mercury's inner core is solid iron, nearly the size of Earth's inner core, despite the whole planet being much smaller. They estimated Mercury's solid inner core to be about 1,260 miles, 2,000 kilometers across, almost mirroring Earth's 1,500-mile inner core. Surrounding that is a molten outer core driving the planet's geology and magnetic field. It's mind-boggling. Mercury is like a tiny ember of a planet with a huge molten metal engine inside. Mercury's interior is still active due to the molten core that powers the planet's weak magnetic field. Mercury's interior has cooled more rapidly than our planet's, explains planetary scientist Antonio Genova. Mercury may help us predict how Earth's magnetic field will change as the core cools. Mercury, in a way, is a fast-forward preview of a cooling planet. Its small size let it lose heat quickly, shrinking the entire planet as we'll see later. But that huge core raises the first big question and hook for our story. What cosmic recipe could produce a planet so disproportionately metallic? Magnetic field mystery. If Mercury is mostly metal, one might expect it to be geologically dead, yet another surprise awaits. Mercury has a global magnetic field. Discovered by Mariner 10 in the 1970s and mapped in detail by MESSENGER, Mercury's field is about 100 times weaker than Earth's at the surface, only housed 1% of Earth's strength, but it's undeniably there. This was a shocker. Mercury is small, just 1/3 Earth's width, and spins very slowly, one rotation every 59 Earth days, conditions under which a planetary dynamo, the circulating liquid metal that generates magnetic fields, shouldn't run very well. Earth's strong magnetic field is powered by its spinning, churning liquid outer core, but Mercury rotates lazily. So how does it maintain a dynamo at all? It shouldn't by conventional wisdom, yet it does. And that's not the end of the magnetic weirdness. Messenger found that Mercury's magnetic field is lopsided, offset about 20% of the planet's radius northward from the core. In other words, the bar magnet inside Mercury isn't centered. It's 500 kilometers off-center toward the North Pole. This makes the magnetic field stronger in the north and weaker in the south. We've got some models to explain this, but it is still not totally understood. It was a very big surprise at the time, said Messenger scientist Larry Nittler, recalling the team's astonishment at Mercury's off-kilter magnetism. Mercury essentially broke the models of how a small planet cools and generates magnetism, forcing scientists to rethink dynamo theory. The consequences of Mercury's magnetic field are dramatic. Because it sits so close to the Sun, Mercury is blasted by the solar wind, a gale of charged particles. Mercury's mini-magnetosphere deflects some of this, but it's small and gets buffeted and compressed severely by the Sun's field. At times, Mercury's magnetic field connects with the solar wind's field to create magnetic tornadoes funneling hot plasma to the surface. When those charged particles slam into Mercury's ground, they knock neutral atoms off into space, contributing to Mercury's ultra-thin atmosphere, more accurately, an exosphere. In effect, Mercury's magnetosphere is a natural laboratory for studying how solar wind interacts with a planet. It's so dynamic that it can change in just minutes, illuminated by Messenger's measurements of fluctuating plasma and energetic electrons around Mercury. From a storytelling perspective, Mercury's magnetic field invites a great visual analogy. Picture a tiny, wobbly magnetic bubble around a scorched planet, fluttering like a candle flame in the solar wind. It's a wonder Mercury's field exists at all. The planet's slow spin and small size make it an unlikely dynamo. Scientists suspect the field is powered by complex core convection, perhaps driven by Mercury's inner core solidifying and sulfur-rich molten outer core circulation, but there's much we don't know. Bepi Colombo's instruments will measure Mercury's magnetosphere in detail to help crack this mystery. For now, Mercury's magnetic field stands as a paradox, a miniature Earth-like magnetosphere on a planet barely bigger than the Moon. One more reason Mercury shouldn't exist in its present state, yet does. A barebones planet. If you were standing on Mercury in a very protective suit, you would experience one of the most extreme environments in the solar system. Mercury has virtually no atmosphere, its gravity is too weak, and the sun's heat too intense to let gases linger. Instead, Mercury wears an ultra-thin exosphere of atoms blasted off its surface by micrometeorites and solar wind particles. It's an airless, exposed world, more like the Moon than like Earth or Venus. This lack of atmosphere means Mercury's surface temperatures swing wildly. Daytime can exceed 800 degrees Fahrenheit, 430 degrees Celsius, under the intense sun, but at night it plummets to negative 290 degrees Fahrenheit, negative 180 degrees Celsius. Mercury goes from oven to deep freeze every Mercury day, which lasts 176 Earth days long. This fierce environment creates some head-spinning phenomena. For example, at Mercury's equator, noon is so hot that some metals would boil, yet just over the horizon it might be hundreds of degrees below zero in darkness. With no atmospheric blanket, heat escapes into space instantly on the night side. In fact, Mercury's surface is so airless and thermally stark that scientists compare it to an extreme physics lab. What you drop on the ground, say sodium atoms from a rock, will literally bounce into space in the weak gravity. Mercury's exosphere is a ghostly mix of atoms like sodium, potassium, calcium, and even a bit of oxygen, constantly replenished and lost to space. It's dynamic too. Glowing sodium gas has been observed swirling and shifting around Mercury, pushed by solar radiation. Yet in this hellish environment, Mercury harbours a sweet surprise. Water ice. Incredibly, the same planet that can fry a spacecraft in sunlight has deposits of frozen water in permanently shadowed craters at its poles. Mercury's axis is almost perfectly upright, only about a 2-degree tilt, so deep craters near the poles never see sunlight. Decades ago, Earth-based radar detected highly reflective patches at Mercury's poles, hinting at ice. MESSENGER confirmed this by directly measuring excess hydrogen and reflectance. Thick deposits of water ice lurk in polar craters like Prokofiev and Kandinsky. These are among the coldest places in the solar system, despite being on the closest planet to the Sun. They never warm above negative 170 degrees Celsius. It's a wonderful juxtaposition. Mercury is a world of fire and ice. Mercury's lack of atmosphere also means meteorites crash unimpeded, pockmarking the surface with craters reminiscent of our moons. Indeed, Mercury's grey, heavily cratered appearance fooled astronomers for years. Until 1965, many thought Mercury was tidally locked, always showing one face to the Sun, and thus one side fried, one side frozen. We later learned Mercury rotates 3 times for every 2 orbits, 3-to-2 resonance, and MESSENGER's global mapping revealed a landscape of impact basins, lava-flooded plains, and curious bright hollows. No air means no weather or erosion, so craters stay for billions of years. This sets the stage for Mercury's next oddity. It's not just static craters, the planet itself has wrinkled and cracked as it shrank, leaving cliffs across those craters. The incredible shrinking planet. Yes, Mercury is literally shrinking, a planet with wrinkles. As Mercury's oversized iron core slowly cools, the whole planet contracts. The evidence? Enormous lobarty scarps, cliff-like thrust faults, snake across Mercury's surface, cutting through craters and plains. These scarps are the telltale wrinkles of a desiccating apple. Planetary geologists have deduced that Mercury's radius has shrunk by about 7 kilometers total over its history. Imagine a world getting measurably smaller. That's Mercury over the last approximately 4 billion years. Mercury is the only inner planet other than Earth that is tectonically active, albeit in a one-plate shrinking sense. As one article vividly put it, this is like the wrinkles that form on an apple as it ages, except an apple shrivels by drying out, whereas Mercury contracts from thermal cooling. MESSENGER's cameras imaged thousands of these lobate scarps, some hundreds of miles long and up to a mile high, thrusting one block of crust over another. They are Mercury's version of mountain building, but driven by planetary contraction, not plate tectonics. The first scarps were spotted by Mariner 10 in 1974, but MESSENGER found many more globally, confirming Mercury's shrinkage was greater than previously thought. Estimates jumped from about 1 to 2 kilometers to up to 7 kilometers radius change. Recent research even suggests Mercury may still be contracting today. Some scarps show tiny troughs or grebens on their crests, like little tension cracks that appear fresh and undegraded. These likely formed in the last few 100 million years, practically yesterday in geologic time, as the crust continued to buckle. If so, Mercury might still be rumbling with the occasional giant Mercury quake as the planet cools further. It gives Mercury a distinction. Along with Earth, it's one of the only tectonically active terrestrial planets right now, albeit a very different style of tectonics. How do you make a Mercury? All these bizarre traits beg the question, how did Mercury end up this way? A tiny planet with a giant iron core, a thin rocky rind, unexpected volatiles, and a magnetic field, it's a planetary oddball. Planetary scientists have proposed several dramatic origin stories for Mercury, each like a puzzle piece attempting to explain one aspect or another. The giant impact hypothesis. Mercury as a stripped core. The leading traditional idea is that Mercury started larger and Earth-like, with a silicate mantle and iron core proportional to other planets, but suffered a colossal impact early on. Imagine Mercury 1.0 as a Mars-sized protoplanet, then an Earth-sized body or a massive asteroid slams into it, blasting away most of Mercury's rocky outer layers and leaving behind an oversized iron core remnant, the Mercury we see today. It's analogous to how the Earth's moon likely formed, a giant impact ejecting debris, but in Mercury's case the impact debris mostly escaped or reaccreted elsewhere, rather than reforming a moon. This hypothesis intuitively explains Mercury's big core and high density. However, it raises a conundrum. Normally, if you blast material off a planet, a lot of it might fall back. Calculations showed that debris from a Mercury impact would tend to remain in Mercury's orbital zone and fall back to reform much of the lost mantle within millions of years. So how did Mercury stay metal-rich? Enter a clever twist: the early sun's hyperactive solar wind. Recent work by Christopher Spaulding and Fred Adams in 2020 suggests that the young sun's solar wind was 10 to 100 times stronger than today, due to the sun's faster rotation and stronger magnetism back then. This intense outflow of particles would act like a cosmic leaf blower. Spaulding and Adams calculated that if Mercury's mantle were blasted into a cloud of debris, the dense young solar wind would swiftly drag those fragments outward, clearing them from Mercury's orbit in under 1 million years. In other words, a giant impact plus a powerful solar wind could strip Mercury's mantle and prevent the debris from reaccreting onto Mercury. Mercury would be left as essentially the iron core of the original proto-Mercury, a cannonball planet. It's a dramatic story. A nameless, rampaging proto-planet sideswipes Mercury, and the raging young sun's wind conspires to scour away Mercury's outer layers, yielding the dense world we know. However, one issue remained. Mercury's surface has surprisingly abundant volatile elements, like sulfur, potassium, that a high energy impact should have depleted, which leads to the next theory. Hit-and-run collisions, inefficient accretion. A variation on the impact idea posits that Mercury's formation involved multiple glancing collisions rather than one big smash. Planetary scientist Eric Asfog suggested Mercury could be a relic of inefficient accretion, meaning Mercury tried to grow like a normal planet, but kept getting sideswiped by other bodies, losing chunks of its mantle in each encounter, and never fully coalescing like Earth or Venus. In this scenario, Mercury might have formed further out, with more volatile, rich material, then migrated inward, getting whittled down by collisions on the way. A key point is that hit-and-run impacts could strip mantle while allowing Mercury to retain some volatile, rich material rather than vaporizing it all. This might explain why Mercury's surface today is rich in volatile elements, like up to 4% sulfur by weight. A lot. Yet the planet is iron-dominated. It's a bit like Mercury survived multiple near-fatal accidents, a battered survivor that made it to the innermost orbit. Could Mercury be the last remnant of a bigger original population of inner system bodies that got destroyed? This paints Mercury as a lone survivor, perhaps explaining its loneliness. Mercury has no moons, and it's far from any comparable-sized neighbour. Solar vaporization or evaporation. Hypothesis. An older idea suggested Mercury's proximity to the young sun might have caused intense heating or even vaporization of its outer layers. In the blazing inner solar nebula, perhaps the sun's heat could only allow refractory materials, metals, to condense at Mercury's location, or later the sun's radiation boiled off Mercury's mantle. However, this idea fell out of favour because Mercury's unexpected volatile element content doesn't match a superheated origin. If Mercury had been baked or evaporated, elements like potassium or sulfur should be severely depleted, yet Messenger found them in surprisingly high concentrations on Mercury's surface. In short, Mercury looks chemically more like a cooler planet, even akin to Mars in some elements, than a torched cinder. So pure solar cooking can't be the whole story, though solar influence likely played some role in clearing debris. Magnetic sun disk hypothesis, magnetic sorting of material. A fascinating new idea, 2021, posits that Mercury's large core is a result of where it formed in the sun's magnetic field. Researchers William McDonough and Takashi Yoshizaki proposed that in the early solar nebula, the sun's strong magnetic field pulled iron grains inward toward the center. In the disk of gas and dust, tiny magnetic iron particles would drift sunward, enriching the innermost region with extra iron. Thus, Mercury formed in a zone rich in iron thanks to the sun's magnetism, whereas Mars formed farther out in a zone depleted of iron. Hence, Mars has a small core. This model neatly explains a gradient. Mercury ended up around 75% metal by mass, Earth and Venus about 30%, Mars only about 25%. It doesn't require violent impacts at all, just physics in the proto-planetary disk. Essentially, Mercury's big iron core might be a direct imprint of the young sun's magnetic influence, acting like a cosmic iron sifter. This theory is still new and being evaluated, but it offers a peaceful formation story that contrasts with the smash-up scenarios. Each of these theories has pros and cons, and it's possible the truth is a combination. Perhaps Mercury's formation conditions gave it extra iron, and it had a mantle-stripping collision. The ongoing mystery is part of what makes Mercury so compelling. Scientists are eagerly awaiting more data, especially from Bepi Colombo, to test these ideas. For example, by precisely measuring Mercury's composition, including isotopes, to see if they match impact predictions or disk predictions. Could Mercury be the exposed core of a lost sibling planet, or is it a product of a unique birth environment near the Sun? It's a tantalizing mystery that connects to broader themes. Understanding Mercury helps us figure out how common or rare such iron-rich planets might be in the universe. Notably, exoplanet hunters have found some super Mercuries out there, dense, iron-heavy worlds, so Mercury may be a key to deciphering those as well. Mission. For decades, Mercury was poorly understood. Only half its surface had even been seen, from the Mariner 10 flybys in the 1970s. Enter NASA's Messenger mission, 2008 to 2015, which orbited Mercury and completely rewrote the book on our understanding of Mercury, in the words of Deputy PI Larry Nittler. Messenger, Mercury surface, space environment, geochemistry and ranging, was a game changer, providing a flood of data that answered some questions but raised new ones. Here are the highlights of what Messenger found. Mapped the entire surface. Messenger mapped 100% of Mercury's surface in color and stereo. It revealed a world of ancient craters and surprisingly young geology. We saw magnificent features like the Calores Basin, one of the largest impact basins in the solar system at approximately 1,550 kilometers across, surrounded by strange hilly and lineated terrain likely jumbled by the shockwave. We also saw evidence of extensive volcanism. Large portions of Mercury's surface, the smooth plains, are flood basalts, where runny lava covered old craters. One giant volcanic deposit called Nather Facula turned out to be the site of Mercury's largest known pyroclastic volcanic explosion, with a 40-kilometer wide volcanic vent and bright deposits 300 kilometers across. This told us Mercury wasn't just a dead rock after formation. It had a lively youth with eruptions and lava flows up until at least 3.5 billion years ago, and maybe minor volcanism after discovered hollows. One of Messenger's most unique discoveries were bright shallow depressions found all over Mercury's surface, dubbed hollows. These look like irregular rimless pits, often on crater floors or central peaks, with high reflectance, bright material, and bluish color enhanced color images. Hollows appear to be places where something has sublimated or outgassed from the rocks, leaving voids and causing the surface to collapse. They are geologically young, they have fresh, uncrated appearances, and might still be forming. Scientists think hollows could form by volatiles like sulfur or chlorine being heated by the sun and escaping, literally creating little sinkholes. Mercury's hollows are unlike anything on the Moon or other planets, a true Mercury specialty. They show that even without atmosphere, Mercury's surface can change in real time due to solar heating and chemistry, like dry ice sublimating and leaving pits in a block. Mercury's rock might have unstable ingredients that evaporate in vacuum, leaving these bright pits. Verified water ice at the poles. Messenger confirmed that the radar bright patches in polar craters are indeed water ice, covered by an insulating layer of organic rich dark material. Using neutron spectroscopy, it measured hydrogen concentrations consistent with thick ice deposits. For example, inside the crater Prokofiev, near Mercury's North Pole, there's a sizable ice sheet on the floor. It's an amazing thought, billion-year-old frozen water on the closest planet to the Sun, likely delivered by comets or water-rich asteroids long ago and trapped in the perpetual dark. Elemental composition shake-up. Perhaps Messenger's biggest surprise was Mercury's surface chemistry. By using X-ray and gamma-ray spectrometers, Messenger measured the abundance of elements in Mercury's crust. It found high amounts of sulfur, sodium, potassium and chlorine, and relatively low amounts of iron in the surface rocks. This was a huge surprise. Conventional wisdom said the innermost planet should be depleted in volatiles and enriched in refractories. Instead, Mercury's crust looked more like that of a mid-range planet, or even Mars in some ways, with volatiles intact. For example, Mercury's potassium-thorium ratio, a measure of volatile retention, is similar to Mars, not drastically lower. And the surface iron is low, implying most of Mercury's iron is indeed in the core, consistent with the big core. These findings negated many previously held ideas about its early development, noted Sean Solomon. Mercury's unexpected composition is a key clue to its formation, spurring the new theories we discussed, like the magnetic sorting idea. As Nittler said, the new understanding of Mercury's composition provided essential clues to how Mercury formed and has been crucial to building modern theories of solar system formation. Mercury's active magnetosphere. Messenger mapped Mercury's magnetic field in detail and confirmed its dipole in nature and northern offset. It also observed phenomena like magnetic substorms, particle bursts, and X-ray emissions from the surface when solar flares cause particles to hit, essentially X-ray fluorescence of Mercury's surface during solar events. Mercury's magnetosphere might be small, but it's dynamic and lively, giving us insight into space weather on a planet with almost no atmosphere to shield it. This has practical implications too. Any future Mercury landers or bases would need to handle intense radiation and magnetic fluctuations. Interior structure and solid inner core. As mentioned earlier, by tracking the slight wobble, libration of Mercury and the spacecraft's orbit, Messenger was able to determine the moment of inertia of Mercury and confirm the existence of a liquid outer core and solid inner core. In 2019, scientists announced the evidence for Mercury's solid inner core, making Mercury only the second planet after Earth, with a confirmed solid core inside a liquid metal layer. This tells us the core is still cooling and crystallizing. It also underscores that Mercury's core is not only huge but Earth-like in having a solid center. The dynamo likely comes from the liquid part circulating around that solid seed. Tectonics and recent activity. By imaging the surface at high resolution, Messenger found small-scale tectonic landforms too, tiny scarps, only tens of meters high, that cut young craters, hinting at very recent contraction. These suggest Mercury's interior isn't done shrinking. It's possible Mercury still experiences the occasional seismic slip on these faults. Messenger, in essence, found Mercury to be geologically double-sided. On one hand, ancient and heavily cratered, on the other hand, still evolving, cooling and cracking today. In summary, Messenger turned Mercury from an enigma we'd seen only in part to a rich world full of surprises. It answered decades-old questions. Yes, there's ice. Yes, big core confirmed. But also uncovered new mysteries. Why so many volatiles? What's with the magnetic offset? Are hollows still forming? The Messenger mission's achievements form a satisfying middle act. We went from ignorance to insight, but the story isn't finished. And that leads to the current chapter, what we're doing now and next to solve Mercury's remaining riddles. Bepi Colombo and the next chapter of Mercury exploration. The exploration of Mercury continues with Bepi Colombo, a joint mission of the European Space Agency, ESA, and JAXA, Japan, on its way to Mercury right now. Launched in 2018, Bepi Colombo is actually two orbiters in one, ESA's Mercury Planetary Orbiter, MPO, and JAXA's Mercury Magnetospheric Orbiter, nicknamed MIO. They are stacked together with a transfer module during the cruise. Bepi Colombo has to perform a complex series of 9 gravity-assist flybys at Earth, Venus, and Mercury to slow down enough to orbit Mercury. Mercury is notoriously hard to get to because it's so deep in the Sun's gravity well. After a 7-year journey, including 6 Mercury flybys, Bepi Colombo will arrive in Mercury orbit in late 2026, recently adjusted from 2025 due to a thruster glitch, with the science mission to begin in early 2027. Even though it hasn't entered orbit yet, Bepi Colombo's flybys have already given us new perspectives. During its close passes, some within 200 kilometers of the surface, Bepi Colombo snapped images with its monitoring cameras, capturing dramatic shots of Mercury's cratered horizon, and even glimpsing the South Pole for the first time on a recent flyby. It also made the first observations of Mercury in the mid-infrared, using the Mercury's instrument during flybys, which will help map surface mineralogy and temperature in unprecedented detail. For example, one ESI release noted that Bepi-Colombo is the first to see Mercury in a new light, literally in thermal infrared, revealing how different rocks cool at night. The flyby images have already highlighted interesting features. Bepi-Colombo peered into the darkness of polar craters, confirming which ones are in permanent shadow where ice can hide. It also captured stunning views of volcanic plains like Borealis Planitia and bright rays of young craters like Kuiper and Hunkal in stark clarity. These are tantalizing hints of what's to come. Once in orbit, Bepi-Colombo's science phase will be the most comprehensive Mercury study yet. Its payload of instruments will measure Mercury's surface composition, geology, magnetic field, magnetosphere, exosphere, interior structure, essentially building on Messenger's legacy with updated technology and two orbiters working in tandem. Some key goals and how they tie to unresolved mysteries. Composition and surface geology. Bepi-Colombo will map the chemistry of Mercury's surface rocks more thoroughly using X-ray, gamma-ray, neutron, and infrared spectrometers. We'll get global maps of elements and minerals which can test theories like the magnetic sorting formation theory. Does Mercury's composition vary with latitude as predicted? And further puzzle out how Mercury's crust formed. BPI could identify rock types and perhaps find remnants of Mercury's ancient magma ocean or volcanic vents. Its high-resolution camera will also image small features like hollows to see if they differ in composition or have changed since Messenger. Imagine detecting new hollows or expansions of old ones over a decade. Interior structure and gravity. Using radio tracking and altimeters, Bepi-Colombo will refine Mercury's gravity field and libration measurements. This can improve our knowledge of the core's size, state, and even test Einstein's relativity in Mercury's gravitational field. There's a planned experiment for that. It might detect small gravity anomalies hinting at interior structure variations, like remnant mantle convection patterns or denser rock regions. Magnetic field and magnetosphere. Bepi-Colombo's two orbiters allow simultaneous measurements of the magnetic field at different locations, a huge advantage for understanding Mercury's magnetosphere dynamics. Mayo JAXA's orbiter is dedicated to plasma and magnetic studies. It will sample Mercury's magnetotail, solar-wind interactions, and charged particle environment extensively. We hope to learn why Mercury's magnetic dipole is offset. Is it something weird about the core's shape or composition, or due to asymmetry in the dynamo? By measuring how the magnetic field changes with time and solar activity, we can also understand how Mercury's magnetosphere responds. E.g., does Mercury have auroras of any sort, like X-ray aurora from charged particles hitting surface? Messenger saw hints of X-ray emission. Exosphere and space weather. Bepi-Colombo will examine Mercury's thin exosphere by directly sampling particles and using spectrometers to detect atmospheric species. It will track how the exosphere's density changes with Mercury's position, solar wind conditions, and even meteoroid streams. This will clarify how Mercury's surface and space environment interact. Essentially, Mercury has a surface-bounded exosphere that is a testbed for understanding surfaces of airless bodies and how they lose material. It's also practically useful. If we ever send landers, we need to know the exosphere composition to avoid contamination or understand drag. Polar ice and surface temperature. Bepi-Colombo carries a thermal infrared camera that can map surface temperatures day and night, which can confirm which craters are cold traps and how cold they get. It might even directly detect water ice or frost at the surface of some polar craters by their spectral signature. This ties into the question of how water and other volatiles got to Mercury and how they persist. We might find out if Mercury's ice has a layer of insulating dust. Messenger hinted at organic rich material covering the ice. Also, by measuring Mercury's thermal inertia, how quickly surfaces heat up or cool down, Bepi can infer regolith properties and perhaps even differences in rock composition. After Bepi-Colombo, we might finally know if Mercury truly is the battered core of a larger body or a marvel of solar sculpting. We might learn how its weird magnetic field works and see Mercury's surface in sharper detail, perhaps even catching changes. The mission will also be emotional for scientists. Many of the messenger team are involved, and it's the culmination of decades of Mercury fascination. Thanks for exploring Mercury with us, the little planet with big secrets. If you learned something today or just love the wonders of space, consider liking this video and subscribing to Cosmo Pulse. We drop videos every Wednesday, Saturday and Sunday that make the cosmos feel closer and stranger than ever. Until next time, look up. Mercury may be tiny, but its mysteries are enormous.